Morning everyone, and welcome to the webinar on the topic Introduction to Frame NVH. I would like to go through the following contents in the webinar, which would be a quick revision of what we have studied in vibrations in our engineering days. Then we'll look into what is NVH, what are the different areas of NVH, and how is NVH applied to a frame. Then what do we do with respect to a frame analysis from NVH point of view, and we break it up into different steps. There is modal analysis, frequency response functions, stiffness and control, etc. And once we are done with that part, we'll focus on what is the FEA approach which is used in the industry, and also we look into certain set of tools which are in demand and which are used in the industry for carrying out NVH analysis. And on concluding remarks, I would like to discuss regarding the industry opportunities for students who are fresh pass outs and what roles they would be playing, and also what all industries they can target for NVH related roles. And then that will be followed up by a Q&A session where I would like to clear most of your doubts related to the NVH area. Yeah, let's start with vibrations. So all of us have studied vibrations, I believe, in our engineering courses. And I also understand that it was probably one of the most difficult subjects to understand. So let me try to give a small revision of vibrations before we go into NVH, because these concepts are very, very essential in going forward to carry out NVH analysis. So vibration in the simplest terms is nothing but a motion that repeats itself from time to time or within an interval of time. And its most simplest representation would be a sine wave. And a sine wave, when you plot it on an x and y axis, you can read it as alternate crests and troughs, and that is how a usual vibration system is visualized in a mechanical engineering world. Coming to the layman terms, if you see around us or if you take the human body itself, you will be surprised to know that vibration plays a very vital role in most of the day-to-day activities. To name a few, we are able to hear only because of vibrations. And how is that? That is because our eardrums vibrate whenever there are sound waves which are going to come and impinge on the eardrums. And the eardrum is going to resonate, and that is going to send signals to the brain. And that is how our brain perceives sound, which is going to affect to us. Then even breathing, for example, if you take, so it is nothing but compression and relaxation of the lungs of the human body. That will also constitute a type of vibration. And even speaking, for that matter, is also a kind of is also an output from the vibration of the larynx in the throat of the human body. So human body itself has so many areas where vibrations are involved. And coming out of the human body, and if you want to look at the surroundings, you can find vibrations in almost every part or every region of it. For examples, there are numerous machines which exhibit vibrations. There are buildings and structures which undergo vibrations. If you take automotive sector, almost all of the automotive sector engines and bodies undergo vibrations. So hence vibration is a very interesting branch of study, and it becomes all the more interesting when you want to analyze a system for a given vibration and how is it going to behave for a given set of forces, what will be the response of the system. So that's a very interesting part of study. And in order to understand vibrations in a better way, what we had studied in engineering was that we can divide the vibration systems into a single degree of freedom system, a 2 degree of freedom system, and multiple degree of freedom systems. And the respective examples for them would be spring mass systems, double pendulum, and a railway wagon. In other terms, if you want to define vibration, you can actually bring in the spring damper analogy, spring mass damper analogy. That is, each and every system or each and every body can be subdivided into a spring, mass, and damper. And by spring, mass, and damper, to speak in very simplistic terms, they are nothing but forms of energies, where spring will represent the potential energy, mass will represent the kinetic energy, and damper will represent the dissipation energy. So what happens usually whenever there is vibration happening is the potential energy and the kinetic energy are interchanging themselves, and the dissipation energy or the damper is going to act as the force or the source which is going to reduce the potential and the kinetic energy in every cycle. So if you can take a look at the image which is on the right, you can see that a pendulum is continuously clocking across the midpoint. So if you see here, when it is at the midpoint, its potential energy is going to be at the highest and the kinetic energy is going to be 0. And let us say if you just strike the pendulum once, then the pendulum is going to start clocking itself. And at the extreme end of it, we can say that the potential energy is going to be 0, but it is going to have maximum kinetic energy. And that is how the potential and the kinetic energies are going to interchange themselves and help the pendulum to keep on rocking. And where does damping come here? So now if this pendulum is allowed to freely rock by itself, then it's going to come to rest after a certain point of time. And that is because of the internal friction forces and also because of the air, which is going to offer resistance to the movement of the pendulum. And that is how damping is perceived in nature. Then some terminologies which we learned with respect to vibrations were natural frequencies, then damping, different equations of motion, what are the different types of free and forced responses. So all of them are nothing but means to characterize the vibratory system. Natural frequencies define the characteristic moments of the system. Then damping will define how good the system is with respect to dissipating the vibration energy. Equations of motions were derived to simplify the actual vibratory system into mathematical models and mathematical terminologies. And the solution of those equations of motion will actually give you the vibration parameters which are needed to solve or which are needed to characterize the system. And we have different types of vibrations, that is, what are free vibrations, what are forced vibrations, how is a system going to behave with a free and a forced vibration, under a free and forced vibrations, etc. And then we also spoke about transmissibility. So whenever there is a vibration set up into a system, there is definitely going to be a force involved. And when the force excites the system is going to vibrate with some energy, and this energy is going to get transmitted to all the connected members of the body. And that is the area of interest which an engineer would be looking into. How much amount of force is getting transmitted to another body? Is that force under limits? How am I going to control that force? Is that force necessary or is it unwanted? So those were the areas which we have studied previously in engineering, and that was a quick brush up of the fundamentals of vibrations and also the terminologies which are used in vibrations. Now let's take a quick look at the NVH perspective of the entire whole thing. So what do you mean by NVH? NVH is an acronym for noise, vibration, and harshness. And why are they used together? Let's come to that. So in the previous slide, when we spoke about a force which is going to induce certain vibration into a machine, what are going to be the side effects or what are going to be the further effects of that forcing function which is going to induce vibrations? In most of the cases, that vibration which is induced into the system is going to interact with the surrounding medium, and it is going to radiate energy into the surrounding medium. And let us say if it is air, that the energy which is radiated into the surrounding medium is going to go in forms of pressure waves. And these pressure waves are nothing but what we call it as sound waves. So vibration is going to give rise to sound, and whatever sound is generated, if it is going to go beyond a level, or if it is going to go beyond the limit of human ear perception, then we call it as noise. So vibration, unwanted vibration is going to lead to unwanted sound, which we call it as noise. And if the unwanted vibrations reaches a peak, or what we call it at resonant frequencies, then it is the sound or the noise which is generated is going to be much more irritating and unpleasant to the human ears. And that is what we call it as harshness. So NVH, that is noise, vibration, and harshness, are all interrelated. The source being the vibration, which is in turn going to generate the noise. And from noise, whatever is the level of perception of the human ear, we can classify it as harshness. So what would an engineer typically do when we say NVH engineer, NVH analyst, etc.? The typical role of an engineer would be to reduce the vibrations at the source so that whatever noise is going to come into the system, that is reduced to an extent, and also in turn that is going to reduce the amount of unpleasant things which the user is going to experience. Also, it can be in a reverse way. Sound source can generate structural vibrations, and that can also be very unpleasant. And that is also another area of study, wherein an acoustic source is going to generate a vibration in the structure. But since we're talking about frame NVH, let's focus on the frame itself acting as a source, as a vibratory source, and also as a path to transfer different forces from one part of the car body to another. So an engineer's duty would be to understand how vibrations are generated, from where the vibrations are going to come onto the frame, and how much of a vibration is too much. There are certain set of standards which the industry uses to identify what level is good and what level is bad, and also how much of sound or noise is required inside an automotive cabin, or how much is the desired level for a human being. So if you can see the images here, the one on the right side, that's the image of a shaker, which is having a forced induced vibration. So if you can make it analogous to something like a cup of water, so that is how the vibrations are going to look if you can transfer those vibrations, or if you keep a glass of water on the shaker, that's how the water would vibrate. So that's the transmissibility which I was talking about in the previous slide. And if you look at the left side here, there's a graph which has two plots in it. So the top one would be called as music because it's quite repetitive and it's quite smooth, whereas the one below it would be called as noise. And that would be our area of interest, wherein we try to reduce this unwanted noise and harshness which are going to get generated because of the undue vibrations in the body. Yeah. So I would like to stick to a car body, a car model, whenever we talk about frame NVH, but you can also extend it to different other areas because the technical concepts and the workflow would almost remain the same. So whenever, let us say you are sitting in a car, and whenever you start the car, so you are going to experience certain vibrations. For example, say at the steering wheel, on the gear pedal, on the clutch pedal, on the floor of the car, etc. So, and also when you close off your windows of the car, and let us say you're cruising at around 80 or 100 kilometers per hour, you are also going to hear some noise inside the car cabin. So there can be different sources of those vibrations as well as noise. So what can they be? It can be a road noise, which are going to get generated because of the rolling of the tires on the road, and then those in turn will be affecting the suspension systems, and the suspension systems will be transferring the energies to the frame, and the frame on which the seats of the car are fixed. So there the driver will be experiencing the vibrations on the seat of the car, and also the steering system is connected to the main body. So the driver will be experiencing certain set of vibrations on the steering wheel, and also the gear, similarly with the gear pedal and the floor of the car. And also all of this in combination will also add to the sound which is going to be experienced inside the cabin of a car. So all of this would constitute the understanding of noise and vibrations inside a car body, inside a car cabin as such. And our area of interest in today's webinar would be to understand what we do to reduce the vibrations in a frame, and how do we go about understanding the different aspects and parameters of analyzing a frame from NVH perspective. So in the previous slide, the image which I had shown was quite simple, and it was for a very layman approach. But for an NVH engineer, whenever we speak about NVH analysis, we'll have to divide the system into different areas or different levels, and then we need to analyze the system and understand the NVH behavior. So usually an automotive component would be divided into different levels, wherein you can just work on only the trim body of the car, which will have only the frame and the body of the car with some other components, or you can start working especially only with sub-components, which we usually call it as a component level or a system level, wherein you analyze a simple component along with its inbound auxiliaries, and also system level, where you define a complete system, and then you try to figure out what are the causes of vibrations, what are the forces which are going to come onto the machine. And also you can have the full vehicle analysis and try to understand how much of vibrations are going to get transferred in a complete vehicle, and what is the sound level which is going to get generated inside the cabin of the car. So in our study now, we are going to talk more about the system level, and here the system under consideration would be the frame of the car, which I would say we usually work with three distinct areas whenever we do analysis of that, and that would be divided broadly into a modal analysis, then a forced response analysis, which involves frequency response functions, and then the vibration control via stiffness, different stiffness methods. Let's start looking at each of them in detail. Modal analysis. So I'm pretty sure that most of you all have heard this term, modal analysis, natural frequencies, mode shapes, and blah blah blah. So let's quickly see what modal analysis is, how important it is to understand the frame NVH, and how is it going to help the engineer to make the frame NVH better. So modal analysis is a broad area wherein we study the component behavior, or we study the behavior of the model under test for its modal characteristics. And by modal characteristics, I mean what are its natural frequencies in a free state, what are its natural frequencies in a constrained state, what frequency will it resonate, what types of displacements it's going to have, what types of movements it is going to have, is it a lateral mode or is it a torsional mode, etc. So when I say natural frequency, it's nothing but the fundamental frequency of the body at which it will start vibrating when you excite it and you leave it. So for example, if you take a guitar, a string of a guitar, you pluck the string of the guitar and you leave it. So the guitar is going to vibrate at a certain frequency, and that frequency is known as the fundamental frequency of the guitar, and that is going to remain constant. So this is very important. The fundamental frequency is a characteristic of the system, or characteristic of the body. So it is like Young's modulus or stiffness. So it is not going to change unless and until you change certain boundary conditions or certain constraints. The natural frequency is going to remain the same, especially in a free analysis. So if you can see the image here, there's a tuning fork which has for which a free run has been given, and it is a constraint has been given, and it is showing its mode shape. So you can see that the two prongs are moving away from each other, and that this is one of the fundamental frequency modes of the tuning fork. Coming to resonance, so whenever any body is subjected to a forcing frequency, and the body has a certain set of natural frequencies associated with it, and the forcing frequency overlaps or matches the fundamental frequency of the body, then the amplitude which is generated will be quite high. And that phenomenon, we call it as resonance. A resonance can be both advantageous and disadvantageous. And with respect to frame NVH concepts, or with respect to frame NVH analysis, I would say we are at a disadvantage whenever we talk about resonance. So this is very important to understand. And we also need to identify at what forcing functions and or what forcing frequencies the resonance is going to happen. Next, coming to mode shape. Mode shape is nothing but the direction of displacement of the body, and which is going to help us understand at a particular frequency in what direction the body is going to displace itself. And that will really help the engineer to make corrections to the design, and to also stiffen the body or make the body more durable, so that the frequencies are not excited and the particular mode shape is not attained. So there are different types of mode shapes, which are the different terminologies being rigid modes. Then you have the lateral modes, you have the torsional modes, you can have vertical mode. There is something called as local and global modes, which usually are applied to the whole body. So global modes are the ones where you can say 85 to 90% of the body is having a displacement, and local are usually where the only one part of the body is going to have certain displacements, that is which is usually observed at higher frequencies, and global modes are of more interest at lower frequencies. The formula for natural frequency mathematically would be given by omega n is equal to root k by m, where k would be the stiffness of the body and m would be the mass of the body, and omega n usually denotes the natural frequency, and omega n would be the undamped natural frequency of the body. So let us quickly try to understand what are these different mode shapes and how do they help us. So if you can see here, plate has been subjected to free analysis, a modal analysis, and these are the different mode shapes which the plate will undergo at different natural frequencies. And each of them, if you plot each of them, those are called as modes. And the mode shapes will help the engineer to understand the behavior of the system better. So in a practical application, let us say you can consider that if this is the frame of the car, okay, and this is the excitation of the first mode, and let us say it has a certain frequency, a single digit frequency of say 4 or 5 hertz, and at this point above it you have located the seat of the driver. So what does this mean is, if the road frequency or say even the excitation frequency from the engines is going to match the frequency which is going to get transmitted to the frame, and it is going to be of 5 hertz, this is the amplitude. The amplitude would be magnified to a greater extent, and the person and the model or the body which is attached to it, that is the seat, would experience very heavy vibrations, and that would cause great discomfort to the driver. And this would be then the area of interest for the engineer to arrest the vibrations of this mode, either move the fundamental frequency to a lower grade or a higher band, and then try to again rerun the analysis and see if the driver's seat is experiencing lower or moderate vibrations which are under the regulated guidelines. Yeah, going further, let's talk more about damping and what is done exactly in a eigenvalue analysis or a modal analysis. So damping is nothing but dissipation of energy from a system, and as discussed in the first slide itself, it's going to play a major role in terms of attenuating the amplitude of vibration. So if you can see the image on the right side here, there are 3 different dampings which are provided. So the first one has a very light damping, the second one has a critical damping, and the third one has heavy damping. What do you mean by those 3 terms? So if the first one, by light damping, it means that the system is free to vibrate, okay, and it is going to come to rest in a slow and a phased manner. And if you can plot a graph of it, this is how the behavior will be, and it will come slowly to rest, okay. And critical damping is the one where the vibration will come to rest in the minimum or the shortest possible time. And that is what you can see here, that the vibration started and then it damped out, and there is no vibration or there is no amplitude. And the third one is heavily damped, okay. So here the rate at which it is going to come to 0 is going to be very, very slow. So all the 3 have different set of applications in the industry. One of the applications for the heavy damping case which I can give is the dampers which we use on the doors in offices. So if you have seen them, whenever you open the door and you leave it jar, so it will come back slowly and it will rest back to its original position. And that is one of the examples of heavily damped system. So critically damped systems, the example which I can give would be those of missile systems, wherein after the missile is shot or after a gunshot, the system has to quickly recoil and come back to its original position. Otherwise, imagine what would happen if it keeps on recoiling like this. The soldiers will never be able to reload it back. So different damping conditions help in arresting the amplitude of vibration to the desired level. So there are different mathematical equations which are formed for the damping. And how is damping going to play a role in analysis? So what we saw in the previous slide was the natural frequency omega n, and that was nothing but is equal to root of k by m. But whenever you talk about damping, damping is going to reduce the natural frequency to a certain level, and that formula is given by the last one here. The damping frequency is going to be omega natural frequency multiplied by root of 1 minus tau of tau square. And what is tau? Tau is nothing but the damping factor divided by the critical damping. And if you closely observe now, critical damping is nothing but a function of constant multiplied by root of, again, mass and spring stiffness. So they're all interrelated. Everything is going to revolve around the mass and stiffness of the body, and damping is going to play an important role as per this equation which is provided. Now coming down to eigenvalue analysis, what are the different types of analysis that can be carried out here in modal analysis? You can carry out a free analysis of the body. So what do you mean by free analysis? Here in a free analysis, there is no forcing function or no force involved. You are just going to allow the body to freely vibrate, and then you are going to figure out what are the natural frequencies of the system and what are the different mode shapes which are going to be exhibited by the system. One of the main applications of a free analysis, especially in an assembly setting, is to understand the model integrity. So let us say you have n number of components of automotive components connected to each other, and if you run a free analysis, you should get 6 rigid modes for the complete component or complete body or the complete assembly of the vehicle. If you get more than that, it means that there is some mismatch in the way we have connected the different components with each other, and that is going to make your complete whole of the analysis to be invalid. So a free run will usually give you the 6 rigid modes, and your 7th mode will be, by rigid modes I mean that the frequency will be almost tending to 0, and from the 7th mode onwards you will have a positive frequency value which will be termed as the first fundamental frequency of the system under test.